Hello again. Today we're going to start talking about how to compute derivatives. This is going to be part one of about 6 parts on which you'll learn how to find derivatives very quickly and easily. You'll probably be very happy not to have to go through and use the limit notation each time you do it. You'll find you'll be able to just write down the derivatives. We'll get to the point where we can do any kind of polynomial today, and then in later talks we'll go on to other kinds of functions there. Before we start, I'd like to introduce sort of a new notation to you. This is called Leibniz Notation, and that's Leibniz, Leibniz, who was one of the people who invented calculus or thought it up along with Isaac Newton. The notation we've been using so far was actually from Lagrange, and that notation, you remember, is y prime or f of x prime, the prime kind of things. Similar to what Newton used. Newton used a dot over the y to indicate the derivative. But the Leibniz notation looks like this. It's a little longer to write, but it's written like this. And that expression is for the time being, that's simply going to be a notation for the derivative. So it's really the same thing as f prime of x, but it's written dy divided by dx. But it's read dy dx. That's why everybody reads it dy dx, and they understand what it means there. And it's best for quite a while now to think of that as simply a symbol that tells you that you're doing the derivative. There's some good reasons for this notation. One thing is it's to remind you that the derivative is a quotient. Comes from doing the limit of a difference quotient always. It has the advantage of being able to identify the dependent and independent variables. The y is the dependent variable in the top, and the x is the independent variable in the bottom. Whereas the f prime notation, because it's used other ways, for example, use f prime at 2 and f prime at 7, you may not know exactly what the variables are. And the third way to look at it, dy dx, it's an operator in the sense that if you wrote dy dx like this, and this is also a good way to use it, and then wrote some function after it, it would tell you that you were then supposed to differentiate that function. And as you'll see a little later, the derivative of that function is very easy. It's 6x. So we're going to be using the Leibniz notation. Excuse me. It's also the way we express the formulas usually. Okay, so we're ready to begin, and we're going to show you where all these things come from. And basically, they come from going back to the limit idea. So if our function, and I'm going to switch notations here back and forth, if our function is f of x equals c, in other words, a constant, then it's very easy to find the limit that gives you the derivative. It's the limit as h approaches 0 of the constant function at any point is c. In other words, the value at x plus h is still c. So the constant function very quickly reduces to 0, and so we have that the derivative, let's write it in the other notation here, the derivative with respect to x of a constant is always 0. Easy enough. All right, the next one that I promised you here was the derivative of x, and again that's a very easy one to do by going back to the limit idea. It's the limit as h approaches 0 of h of x plus h. Remember, the function is just y equals f of x, or y equals x. So it's x plus h minus x over h, which reduces right away to h over h. And I think we can all see that the limit there is 1. So here we have the derivative with respect to x of x is 1. Okay, 2 formulas so far. The third one that we're going to look at is called the a constant times the derivative of a function. So this time the function that we're starting with is some constant times some other function. And so when we again go back to the limit, all these things go back to the limit until we get some of these theorems proved here. We have the limit of the constant times f of x plus h minus the constant times f of x divided by h. That would be applying the derivative rule there. Now, since it's a constant, we can factor it out. And in fact, it can be factored all the way out in front of the limit sign. So it's the constant times the limit as h approaches 0 of f of x plus h minus f of x over h. And of course, that limit that we have there, I hope you all recognize, is the derivative of f. So the answer here is that this is it's equal to constant times the derivative of the function. So again, in the other notation, the derivative with respect to x of a constant times a function is equal to the constant times the derivative of the function. And we'll summarize all these for you in the end when we get to look at some examples. Okay, now comes the big one. All right, and this is called the power rule. All right, the power rule tells you how to differentiate x to a power. And for the purposes of we're starting out here and being able to show you why this is true, we're going to assume that the power is greater than or equal to 1, and also that the power is a counting number, in other words, a positive integer, and belongs to positive integers. Eventually, we'll be able to show that this rule works for any kind of power, positive, negative fractions, anything at all. So, again, we start with the limit as h approaches 0 of f of x plus h, so it'd be x plus h to the n, minus f of x over h. And now we've got to do a little bit of algebra, not too much. We are going to have to expand this x plus h to the nth power. Okay, and I'm going to cheat just a little bit on it, but what we're using is the binomial theorem, and if you remember that, I hope you remember that. The first term, when I expand that, is x to the n. The second term is n times x to the n minus 1 times h, and then here's the fun part. All of the other terms, have in them h to a power, and the power there is greater than or equal to 2. In other words, if you write down all the terms here, remember the powers of h go 0, 1, 2, 3, 4, 5, 6, all the way up to n. So we have terms with h to the n. And I mustn't forget the x to the n on the end to factor off. Okay, now, as you saw in some of the easier examples from the other day, the x to the n cancel out. And all we are left with is all these terms with h in them. So the next thing I'm going to do is cancel out the h's. And remember, it's got to go into each term. So it cancels out here, and then it cancels out here, and this time it gives us now h to a power where the power is bigger than 1 because we've canceled them out. All right, now we're ready to take the limit, and so we will do that right here. It's pretty easy to, oops, wrong color there. It's pretty easy to see what we have. All these terms that have h remaining in them will go to 0 as h goes to 0, and the only thing that's left is this part right here. All right, and so that's our derivative. The derivative is n times x to the n minus 1. And so the summary, the formula that you need to know is that the derivative with respect to x of x to the n is found by taking the exponent times x to 1 less power. That's all there is to it. Just the exponent times x to 1 less power. So that if we were differentiating, say we wanted the derivative of x to the 5th, it would be 5 times x to the 4th. Just the exponent times the variable to 1 less power. The derivative with respect to x of, oh, let's take a good one, x to the 21st is, write it down, 21x to the 20th. That's all there is to it. Okay, so the power rule is important there too. Okay, the final rule we want to look at today is for the sum or difference of two functions. Okay, for the sum or difference of two functions, we'll do the sum here, but the difference comes out the same way. Our starting function is f of x plus g of x, and minus will work pretty much the same way. So we start again with the limit as h approaches 0 of f of x plus h, and just to make it clear to you here, plus g of x plus h minus f of x plus g of x. And I just put them in color there so that you could separate them out, as we're going to have to do in the next line. So what I'm going to do here is I'm going to, well, I wanted to stay with black here. All right, the limit as h approaches 0 of, and I'm going to take the two f terms out here, and so it's going to be f of x plus h minus f of x over h, and then what's left is plus the limit as h approaches 0 of g of x plus h minus g of x over h. And then I hope we recognize both of those limits, that this is going to be the first limit up here is f prime of x, and the second limit is g prime of x. And so there you have, the final rule here, that the derivative with respect to x of f plus g is equal to the derivative of f plus the derivative of g. And of course, subtracting works the same way. If it were f minus g, there would be a minus sign here and a minus sign here. And then when we factored them out, there would be a minus sign here and here and here, and we'll just make it plus or minus here. So that, let's do it that way all the way through here. Let's erase this a little bit here. So the derivative of f plus or minus g is the derivative of f plus or minus the derivative of g. Okay, and let's just do one or two quick examples here of how you use all these rules together to work on polynomials. We'll start with a fairly simple polynomial. Let's say y here is equal to 3x squared minus 5x plus 2. And we're going to use all these rules together to find dy dx. Okay? The first thing is that we have subtraction and addition. So what that tells us is we can do it term by term by term. We can differentiate 3x squared and then 5x and subtract it, and then finally take the derivative of 2. And that's the way you do it. Now, so we'll concentrate first on the 3x squared. We have a constant 3 times x squared. So the derivative, so we have 3 times the derivative of x squared, which is 2x. And then we have the next one, which is 5 times the derivative of x, and the derivative of x is 1. And then finally we have the derivative of a constant, which is 0. So we'll just make this look a little nicer here. It's 6x minus 5. And of course, very quickly you'll be able to go without this middle step here. With powers like this, it's going to be the power times 3. So it's 3 times 2 is 6x to 1 less power, and negative 5 times the derivative of x is 1, and the derivative of a constant is 0. Okay, let's do a little longer polynomial. Let's say we had 5x to the 5th minus 3x to the 3rd plus 2x to the 7th minus 18, something like that. So the derivative here then is going to be dy dx, and it's going to be equal to 5 times 5 is 25x to the 4th minus 3 times 3 is 9x squared plus 14x to the 6th, and the derivative of 18 is 0. And so, that's how you do a polynomial. And we're just going to take one more here just for practice. Just make this up as I go along here. Y is equal to 18x plus 32x squared minus 5x to the 5th plus 12x to the 12th, whatever we have there. All right. And again, just term by term, dy dx is 18, x to 1 less power is 1, and 2 times 32 is 64x. Let's clear that up so you can read it here. 64x minus 5 times 5 is 10. 5 times 5 is 25, actually. 25x to the 4th plus 144x to the 11th. Just go right across and do them that way. Okay, so to sum up here, you learned from the beginning here that the derivative of a derivative with respect to x of a constant was 0. The derivative of a constant times a function was the constant times the derivative of the function. You learned that the derivative of x with respect to x, or anything with respect to anything, is 1. You learned the power rule, which said that the derivative of x to the n was n times x to the n minus 1. You sort of learned separately one that really makes the same thing, namely that the derivative of x is x. That's the same idea. It's 1 times x to the 1 less power is 0 there. There's your product rule. And then you learned that the derivative of the sum or difference of two functions was the sum or difference of their derivatives. No doubt you have a list in your book somewhere that has those same formulas. If not, be sure you get them down. There's some of the things that do have to be memorized here, and they shouldn't be too bad to memorize because you use them so often. So we'll call it an end there, and look them over. Your teacher will probably have some homework for you, and we will see you again next time. Bye.